Hello, everyone. My name is Jason Molgard. I'm a storage architect at ARM. I'm here to speak to you today about computational storage architecture, simplification, and an evolution. So a quick agenda for today's presentation. Start out by giving an overview of computational storage, just to level set and make sure we're all on the same page. And then kind of launch into a controller hardware architecture discussion, followed by a controller software architecture discussion. And then send us off kind of into the future, thinking about combining CXL and computational storage. And lastly, we'll wrap up. So computational storage overview. Again, this is just to kind of level set so we're all on the same page. So what is computational storage? Well, so if we first start out by taking a look at the traditional model shown over on the left-hand side, traditionally a server would make a request for data from storage. That data would then be moved from the storage to the compute. The compute would then perform some operation on it, and results might optionally be returned back to the storage. That's what we've been using for quite some time, and we're all very familiar with that. But with computational storage, the intent is that the server would make a request for an operation of the storage. The compute would happen on the storage device itself, and the results would be returned back to the server that made that request. There are quite a few benefits that we'll get into in a little bit more in the next slide related to energy efficiency, latency, and potentially security. But certainly you can have data-centric workloads as a result of this. So based upon the type of data that is stored on the drive, then you can make the decision as to what kind of operation should be done on that data and focus exactly on the operation that is needed for that data. So let's look at the benefits a little bit more closely of computational storage. So if we start all the way over on the left-hand side with bandwidth, certainly one of the big goals of computational storage is to reduce data movement. And so if you reduce the amount of data that needs to be sent from the storage to the server, clearly you're going to have bandwidth that's available. It's not going to be needed. That bandwidth can obviously be reallocated for other applications or other purposes. It's never going to go to waste. I suppose optionally, if there really is an abundance, it would be possible to reduce down the number of PCIe lanes on a storage device, or just shut it down altogether if there's no need to be moving data. All of the above are going to save power at the end of the day, and that's certainly a huge thing. By reducing that power, certainly that's going to help with heat in the data center, and likewise help with cost. You're reducing the cost of having to power up all those systems if you're known to have to move as much data. But there's also a cost benefit to having low cost to compute embedded in the storage device, because now you can offload the host. That frees up the host to do other operations and potentially making more hosts available without necessarily having to purchase more hosts. And related to the bandwidth, of course, is the latency. Certainly, there's time to do, whatever function is being done on the drive. But at the same time, if you're able to start the operation more quickly down on the drive, find what you're looking for, and return that result up to the host in the time that it would have taken to otherwise comb through and move all this data over to the host, then you get your results more quickly, thus reducing the latency. And by reducing, the power, the heat, and the data movement, we're clearly going to improve reliability. We're not overtaxing our infrastructure. That's going to have benefits in terms of keeping the systems functioning properly for an extended period of time. And then I've got security listed here. This is a very interesting animal for sure. With security, clearly by adding compute to the storage device, we're opening up new attack surfaces that need to be considered without a doubt. Let's take for an assumption that the folks at SNEA are able to address all that and come up with some great recommendations on exactly how to handle security properly in a computational storage drive. That is certainly something that's being worked on. So if we take that assumption for true, now you can start to think in terms of the fact that we don't have to move plain text user data across from the drive to the host. So you're just keeping the plain text data right there on the drive within the controller of that drive, and likely reducing the chances of somebody trying to intercept it, and hopefully reducing or improving security. So what is SNEA working on? I already mentioned about security. That certainly is a big topic that's under consideration within the computational storage twig. But in addition to that, there's a lot of work that has been put in recently into the architecture spec. There's a 0.8 R0 available now. Likewise, a lot of effort has gone into an API spec. There's a 0.5 R0 that's also available. Both of these you can go freely download from the SNEA website, and I encourage you to do so and provide any comments that you may have as you read through them. So the two diagrams that I'm showing here on this slide are from the various SNEA documents. So all the way over on the right-hand side is a block diagram of a computational storage drive that's within the architecture document. It kind of gives a high-level overview of some of the blocks in that computational storage drive. I'm not going to get into the details of this block in today's talk. If you're interested in those and you're unfamiliar with the terminology there, then I definitely encourage you to take a look at my friend Bill Martin's presentation. He will be going into a lot of detail on this particular diagram and all of the components within it. And on an API, similarly, I don't plan to get into any detail about the API and what's happening with the API. I would suggest that you take a look at my friend Oscar Pinto's presentation, who will be getting into details about the API document. And in both cases, you can learn more about everything that's been going on within SNEA. And there are a lot of folks who are interested in knowing what's going on within SNEA. There are, in computational storage, there are 51 participating companies, 261 member representatives. You can find your favorite company here on this chart. Certainly ARM participates. I happen to be a co-chair for the computational storage twig, and I definitely enjoy helping and working with all of these folks as we try to standardize computational storage. So with that background on what's happening within SNEA and also kind of computational storage in general, let's switch gears a little bit and focus on the controller hardware architecture for computational storage. So as a preface to that, if we take a step back and think about the compute that already exists in a solid state drive today, there's already a significant amount of compute and logic that goes into making SSDs. They're very sophisticated embedded systems by every stretch of the imagination. So in the front end, there's usually, it manages the host interface and the flash translation layer. Typically, there's multiple Cortex R or sometimes Cortex A CPUs that are involved in that logic and data movement. In the back end for flash management, again, a number of Cortex R or possibly Cortex M CPUs, depending on the performance point that a particular SSD is targeting. The diagram shown over here on the right kind of details a lot of these blocks that I'm mentioning. And you'll notice all the way over on the far right-hand side of that diagram, the back-end processor shows two NAND flash channels per back-end processor. Certainly that is valid, but in many cases, it's going to one core per flash channel in order to achieve performance targets. But in addition to those CPUs, there's a significant amount of system IP that goes into that. And I think certainly one of the most important is debug. And in ARM's case, that's the core site debug. Without that visibility, it just is very difficult for the firmware team to develop their code, get that code perfected and bug-free in order to actually ship a product. But in addition to that, certainly there's other components like the interrupt controller, interconnect, you name it, lots of different standardized IP that's required in order to build up a system. But certainly some of the most important pieces are hardware engines. No SSD would be complete without having some dedicated hardware focused specifically on certain functions. So for example, encryption, LDPC, compression, these kinds of functions are best performed in hardware and typically have dedicated hardware engines specifically for those capabilities. And yes, I think that encryption and compression could actually be functions for computational storage. And it certainly applies and makes a lot of sense. And there are folks out there who are using those two types of functions, for example, as computational storage functions. One thing that is for certain is there's a significant amount of DRAM in an SSD to the tune of 1 GB per terabyte of flash. And with drives, reaching 64 terabytes and growing, getting even larger, that means 64 gigabytes of DRAM. That's a significant amount of DRAM on an SSD. Of course, the predominant interface remains PCIe with NVMe. SATA is still out there, and SAS isn't going away anytime soon. I think that later in this conversation, I'm going to mention CXL. That could be an interesting interface that could come up in the future on this interfaces line. So in order to really take advantage and start to modify that block diagram for an SSD and turn it into a computational storage drive, we really want to be able to run a rich operating system, or at least the Linux kernel, to enable eBPF. And so traditionally, if we take a look at the diagram on the right, it's been all predominantly real-time cores, as I had mentioned. Occasionally there's some Cortex A CPUs. But the bottom line is you typically need very low latency, fast response type real-time behavior from the CPU infrastructure in a solid state drive in order to get the performance that is desired. But in order to do the compute, we need to transition a little bit over to the diagram on the right, where we have, in addition to the real-time capability, we want to add in the ability to have Linux kernel with eBPF or full Linux in order to run traditional Linux type applications and perform those computations on the data that's on the drive. So how can you achieve that? Well, certainly the number one thing that's required to be able to run the Linux or the Linux kernel is some type of a memory management unit, an MMU, in order to virtualize memory. The MMU provides that virtualization that those high-level operating systems expect. So there certainly are a number of options for that in terms of different types of ARM cores that are available. All of the Cortex A would support that. And then there's a real-time core that blurs the line between real-time and application. The Cortex R82 has real-time capability and MMU. I can get into a little bit more of that in the next slide. But the bottom line is that there are options for lots of different performance points and with the lowest possible power. So as I had mentioned, some SSD controllers already are using an applications processor for managing their front end or FTL type functions. So for them, migrating to a computational storage drive is an actually very straightforward transition. Not a whole lot needs to change. Maybe they need to consider adding in a few more cores, ensure that they have sufficient compute bandwidth. But from a hardware architecture perspective, it's largely there. Not a lot of change. If a particular controller doesn't already have applications, it's not complicated to integrate and add those in. It can be very straightforward. Certainly could be simplified with the R82 as a drop-in replacement potentially that also then just it provides the MMU capability as well. So for the systems that do have the applications processors already, the SIMD instructions or the Neon provides the ability to run ML type applications more quickly. Certainly that's great when we start thinking about computational storage. May also make sense to have a dedicated ML processor. That's an option as well. I know some folks are also putting FPGAs and other dedicated hardware. I think all of this is a logical solution for computational storage drives, depending on what it is that you're targeting. So as I mentioned, let's take a little closer look at this R82. It really is a great option for implementing a computational storage drive. So the Cortex R82, it is a 64-bit real-time core with a large address map, and provides that real-time capability needed for low latency and consistent performance in a solid-state drive. But it has the memory management unit at the same time. And you can switch back and forth between real-time and MMU contexts as necessary. And in addition to that, there's the ability to have coherency between clusters. So if you find that 8 cores is insufficient, or if you realize that you'd rather split the cores up over a couple of different clusters, you have that capability of having coherency and between those clusters. And it does have those neon SIMD instructions for running ML workloads. So thinking a little bit more about the MMU, plus the memory protection unit, MPU, and how does that work? Well, if we take a look at this diagram over on the right-hand side, essentially at the highest exception level, there's an MPU context. And under that MPU context, you can then instantiate either another MPU context and or an MMU context. And so you can have both running at the same time, and it is conceivable and possible to be running a high-level operating system, receive a real-time interrupt, for example, switch over from Linux to real-time, service that interrupt, and then switch back. The latencies have been optimized to enable that transition. And while that is very interesting, I think that many folks are going to find it more straightforward to simply allocate a core for MMU or MPU, depending upon the function that's required at that time. But the bottom line is, with that flexibility, you can reduce the number of high-cost mask sets and develop multiple products using one controller, and actually, be able to transition back and forth between, those different products. So if you have a classic enterprise drive, as shown over here on the left-hand side of this slide, that would be traditionally all real-time, you can certainly make that with one controller, or you can make a separate product that is a computational storage and has the ability to run a high-level operating system in addition to the real-time for managing the data through the NAND. And beyond that, there's an even greater flexibility in that you can reallocate dynamically as the workload changes over the course of the day. Maybe during the day, the drive is very busy ingesting data, and all of the majority, if not all of the cores are required to help ensure proper real-time response of the SSD functions, and no compute is able to happen at that time. But then later on, the time the drive slows down, maybe it's nighttime and there's more availability for the system and not as much data coming in, and you can reboot some of those cores into running a high-level operating system or the Linux kernel. So then you can then start doing the compute on the data, or increase the amount of compute that can be done on the data. And all this can be happen dynamically as the day changes and the workloads change across the day. So now let me kind of switch gears a little bit and talk a little bit about computational storage drive controller software. So I think that from a software perspective, certainly the ability to run Linux on a storage device, it opens up a whole new range of tools and technologies that weren't traditionally available to a bare metal implementation. And all of these tools and technologies have been ported and optimized to run on ARM cores and just simply work. And with that familiarity, it enables software developers to simply pick up what they know and start developing and innovate and deploy and come up with great solutions very quickly and easily. And I think that's a very attractive combination to be able to leverage what everybody already knows and is already familiar with. But one of the complaints that I frequently hear is, how could we possibly run Linux in our drive that seems so large? Well, certainly agreed you could run as simple as the Linux kernel and in order to enable eBPF, but I would suggest that there are even better options as well. The one such is called the Yakto project. So this is not a new distribution. This is just a way to help developers build embedded distributions easily. So you can use it. Uses a layered model for collaboration and code reuse, and modularity for optimization of speed, footprint, and memory utilization. So in other words, with Yakto project, you can come up with an embedded, small, succinct Linux distribution that is exactly what's needed for a computational storage drive, still using all of the open source software, the kernel, everything that is familiar in the Linux community. And now suddenly it's right-sized for running on a computational storage drive, and just alleviates those concerns about having potentially a large Linux distribution on the drive. So one of the other initiatives that's being driven heavily at ARM is Project Cassini. And there's kind of three pillars to Project Cassini. So standards, security, and ecosystem. And all three of these combined make up this project. So from a standard standpoint, the intent is to leverage industry standards. We don't want to invent new things. And the system ready standard is essentially an ARM standard on how to develop the CPU subsystem and the firmware to have a consistent, known working system that will just come up and boot traditional Linux distributions and work, and not have to have a lot of custom code development or upstreaming or anything of that sort. And so it specifies these different bands, and I will get into a little bit more detail about the bands in an upcoming slide. But how to integrate the hardware, what kind of firmware you should run, and what it would look like, and a certification program, so that if it's all compliant, then you essentially are getting a rubber stamp that, yep, this system is just going to boot and it's going to run existing open source software, no problem. And of course, as with everything, security is a hot topic these days. And so certainly that needs to be secure and compliant with security standards. And then obviously, from a development perspective, folks want to be able to develop in the cloud. They want to be able to leverage what's out there, and then make that software available open source to others as well. And so combine those three pillars, implement this project, and will help simplify the development of your code so you can focus on your computational storage drive. And to that effect, essentially what we're wanting to do is unify those lower level software stacks across those computational storage devices, so that we can reduce fragmentation, provide design patterns that you can say, follow this pattern, and you're going to have a recipe for success. And that's exactly the goal. So it builds upon this system ready in terms of being able to say, here's the hardware suggested recommended procedure or recipe for how to build something, and then of course the firmware on which to get that system up and running. And there's all kinds of different classes, and we'll, like I said, look at those in the next slide. But the bottom line is that there's one to fit everything, including one for computational storage. And then with those kind of software design patterns or templates, it's very understandable as to how you can then start building your custom code and go on top of that and actually get something up and running very easily. And so by leveraging the system ready compliance, it makes software easy to deploy, easy to develop. The OS is simply going to boot and work, and along with all the applications. And that's exactly what we want to enable for those computational storage drives, so that you're not frustrated trying to get a Linux distribution up and running. So here are these system ready bands. There are 4 bands that exist today. If we kind of start at the bottom and work our way up, we certainly don't want to reinvent any wheels. We want to leverage industry standards. So from a device management functionality using OOB, Redfish, the existing standards. We want to take advantage of that as much as possible. And then layer on top of that the ARM CPU integrated according to a recipe specific for the application of interest. So if we kind of focus on the third column from the left where it's labeled System Ready ES, I think this is kind of a logical choice for a computational storage drive. And certainly there's some variability for everyone. But if you kind of follow the recipe for the hardware and the firmware, the system simply is going to boot, and then you can differentiate completely and fully with the OS and applications and middleware and the actual computational storage function that's unique and specific to your drive, your product. And so kind of looking across all these bands, I think you can agree that that's really where the differentiation starts to happen, is above the firmware layers. So the rest of it is, in many respects, is just kind of boilerplate. Here's the hardware that needs to be integrated. Here's the firmware to get that hardware to boot. And then now things start to really become unique and original above that. So combining System Ready and Yakto is really important because I had mentioned Yakto as a way to get an embedded Linux distribution that's small, succinct, and sized appropriately for a computational storage drive. But it also is going to be System Ready compliant, so it's going to work. You don't have to worry about porting software or writing code to get it up and running. It's just you're going to work. You can focus instead on differentiating your features and enabling deployments and streamlining the development and things that are going to be appropriate for your computational storage drive, and helping to get that drive up and running and functioning. And once that drive is up and running and functioning, then you can really start taking advantage of a lot of the other open source software that's already out there. There's many different examples listed here, and certainly there are many more out there. But all of these types of applications have been ported and optimized for ARM and would theoretically be able to run on a computational storage drive if that makes sense for your particular application. I've mentioned eBPF a few times, so it's very important that we touch on that. Certainly there's a lot of interest and activity around eBPF these days, so we don't want to ignore it. If you want to know exactly what's happening with eBPF as it relates to what's happening over in NVMe, then I would direct you to a presentation from my friends Kim Malone and Stephen Bates, who are kind of giving an update on that. So I won't get into those details, but I will say that eBPF certainly runs on ARM cores. It can certainly run in kernel space, and this is why you would need that ability to run Linux, or at least the Linux kernel, for running eBPF. You certainly can run it in user space as well, but you're still going to need to have some way to have some kind of a high-level operating system with the MMU in order to be able to run that. We have done some performance measurements with eBPF running on various ARM cores, and we do see some benefits that are realized by having eBPF running in kernel space especially. But there are challenges, without a doubt. If you're familiar with C, you probably will find that it's less flexible. There's a little bit more difficult to do some of the things that you could do in C that eBPF maybe doesn't support. And of course, that's by design, right? It's running in the kernel. You don't want to allow anything rogue to happen in the kernel, or have unbounded loops in the kernel, for example, that would potentially cause that system to hang and not be able to finish. But even as such, I would suggest that security still remains a key concern, even with eBPF, just because you never know what kind of rogue eBPF program could be developed and deployed to a drive, and we need to mitigate against that, especially if it was some kind of eBPF program with a denial of service that's trying to just lock up all the resources and make them unavailable for other actual legitimate workloads. So as a result of that, ARM is actively optimizing eBPF and looking at how can these types of security questions be addressed. and resolved so that running eBPF on the drive is of no concern because we've gotten a known good working solution to have it up and running. So now let me switch gears a little bit. We've taken a look at the hardware architecture, the software architecture for computational storage drives, and now I want to kind of think about well into the future. Where could computational storage be heading? And I think that CXL plays a big role in that. So I would suggest to you that a computational storage drive is an accelerator with storage. It happens to have storage, obviously. So CXL is designed to interface to accelerators. That was certainly one of the design intents behind CXL. And it is definitely gaining momentum as an interface for coherently connected devices. We're seeing a lot of interest in CXL as it relates to memory disaggregation, memory expansion, memory pooling, that type of functionality. So it'd be CXL Type 3 devices. And so there's a lot of folks out there that are giving a lot of attention to that and what exactly they want to do in that space. But then along comes persistent memory, and it's really blurring the line between what is memory and what is storage. So now suddenly, if you've got this memory expansion device connected up over CXL that happens to be persistent memory, is it really memory or is it storage now? So that's a very interesting question. And that's why I think that CXL is a very natural technology to enhance the CSD capabilities. Certainly down the road, it will take a little bit of time for sure. And I think that it can help accelerate the deployment of CSDs at scale in due time. So over here on the right-hand side is this architecture diagram from the computational storage architecture spec again. And what I want to point out is that there's nothing in the diagram or in the spec for that matter that precludes the use of CXL as the fabric. In fact, the architecture document is very fabric agnostic. It uses the word fabric in the gray that's connecting the computational storage drive to the hosts depicted in the diagram. Yes, it does list a couple of known fabrics, PCIe and Ethernet, for example, but it doesn't specify that either of those are required. So, why not add CXL to that list? It certainly could be. And actually, since CXL is simply a different protocol running on the PCIe physical layer, then it really applies. It's very applicable. So if we kind of step one level deeper into the architecture of what this might look like, over on the left-hand side, we've got a compute server with a CPU SoC in blue, and it has a couple of different CXL ports. So one port is connected up to a yellow block that's labeled storage class memory CXL Type 3 device. This would be like a memory expansion type device. And then there's a green block that's labeled as a Type 1 or a Type 2 accelerator. So I would suggest that this could be a computational storage drive in the future. And so we've kind of expanded that green block to the larger diagram on the right that essentially shows in the very large gray block over on the far right, device vendor logic is how it's labeled, but that would be the computational storage drive and the functions that we are familiar with today. And then in the dash box is everything needed to essentially connect from a third-party CXL endpoint IP into the device vendor logic and implement a complete CXL-based computational storage drive. So if we kind of delve a little bit deeper into that in terms of the architecture, here's a more detailed diagram that could represent a computational storage drive at a lower level. And you'll notice a couple of things here. First of all, I've put a dashed purple block labeled coherent around the DDR controller and memory, and as well as the CXL interface that's heading off to the host. So this could become a Type 3 device. This, in fact, could even be the Type 3 memory expansion device that I had mentioned previously. And essentially, through this DDR, it would enable the host to perform CXL type coherent transactions to the memory. and either way, reads or writes. It doesn't mean that the host couldn't also use NVMe to continue accessing the storage in a traditional manner. In fact, I really expect that NVMe should run over CXL.io with no problem at all. But it provides certainly a new means and a stepping stone to a larger vision with CXL connected to computational storage. And so that larger vision is shown here on this slide, where I've grown this light purple block to include the flash translation layer and computational storage processors. So essentially, this could become a type 2 device with memory. It has, still the capabilities of step 1 that I showed on the previous slide, but now there's the ability for the host to coherently interact with the compute, to dispatch workloads to the compute, to offload workloads to the compute that is in the drive, exactly as CXL was intended. And as a matter of fact, I would suggest that it may even be possible to not only connect these devices, but then use that to move workloads back and forth between the drives and the host. So you could decide this particular workload runs best on the host or it runs best on the drive. You can run them on either place. You can move them back and forth based upon, if you need more performance than the drive is providing, or vice versa. And a lot of that is enabled by the fact that they're both running the same operating system, the same applications and same software stack, both the host and the device, same open source, Linux software, for example. And you can now run those workloads wherever you're going to get the most benefit. And in fact, as kind of a future step, it may even be possible to split workloads between the computational storage drive and the host CPUs, where maybe you have a small part of a workload that runs on the drive and the rest of the workload that runs on the host. And together, the host aggregates all the actual completed computations together to perform a full compute effort. So we already have, split FTL or zone namespaces, as we're all familiar with today. That's kind of an example of where we're splitting the workload between the host and the drive. And so this same type of model could be used for splitting workloads between the host and a computational storage drive in the future using CXL. I already mentioned that I think NVMe would already run over CXL.io today. And so that certainly is valid, but maybe down the road, there's some consideration given to how can NVMe take advantage of the capabilities of CXL. And or maybe even as an industry, we decide, hey, we're going to go a completely different direction, and we want to really leverage the CXL byte addressing capability and interface with our drives in a completely different way. I don't know. I think that's certainly something that the industry would have to decide as a whole, and it will be interesting to see how that plays out as time moves on. So now let me kind of conclude my talk today. So first of all, computational storage is happening now, and there are many benefits to computational storage, and I sincerely hope you are involved in considering how your computational storage drive is going to look, or what it's going to provide, or capabilities that it will have. The SNEA specs are progressing well. If you haven't already downloaded a copy of the architecture document and the API, then please do so and read it and provide feedback if you've got any questions or comments or input. I know for certain that the SNEA would welcome that, and see if we can't answer those and refine and just generally improve it. But once you do read that, I think you'll agree that the hardware and the software require flexibility in order to actually get a good computational storage drive developed. On the hardware side, you want to be able to have the ability to run different workloads and enable multiple products from one controller. They're very expensive to tape out. They're very time consuming to develop, and very sophisticated amounts of logic that go into them. So leverage it as much as possible. And then likewise, you want software stacks that are going to be easy to use, easy to develop, and leverage industry standards. Nobody wants to reinvent the wheel. We all want to use what's out there and take advantage of the open source software community that's available. And you want to be able to dynamically balance, real-time and Linux workloads on your architecture, on your hardware, so that you can dynamically adjust between real-time and those workloads as necessary throughout the day, so that you can perform the best possible response to ordinary SSD functions, while at the same time performing compute on the data. And then looking a little bit more in the future, I think that CSDs can leverage the CXL protocol, and it is just an accelerator at the end of the day. That's definitely down the road, but certainly some interesting food for thought. But I think that for all of these things, whether it's your computational storage drive or CXL, there's a significant amount of development and work still required. And I would welcome the opportunity to speak to you and consider different architectural options and what you're looking at. And I'd be happy to share what I'm working on and see if we can collaborate to bring these new ideas to fruition, to help move the whole industry in a exciting new direction with computational storage and even CXL. So with that, my name is Jason Molgard. I really appreciate you joining this presentation today, and I hope you have a wonderful day. Thank you very much.